Welcome to AP Chemistry at Hononegah High School. Today we're wrapping up our chapter on kinetics. So this is really the fifth part of a five-part series. Today we're going to look at sections 14.6 and 14.7, reaction mechanisms and catalysts. Now, reactions may occur all at once or through a series of several discrete steps. Now, if it's a multi-step process that it actually happens under, each of these processes is known as an elementary reaction, elementary step, or elementary process. So there's several words we can use to basically mean the same thing, a simple individual step. Now, most reactions actually occur not as one overall reaction, but as a series of individual steps, except for very simple reactions. And that's because of collision theory. Remember, reactions can only happen if you have a collision. And when you take a look at the combustion of octane, for instance, two octane molecules reacting with 25 oxygen molecules, what that would really imply by collisions is that two molecules are colliding simultaneously with 25 other oxygen molecules. That's highly unlikely that that is the mechanism with which that reaction actually occurs. So most reactions we looked at, most molecular reactions, are actually an overall reaction. And to really understand what's happening and to influence the reaction, make it go faster, make it go slower, and so forth, what we really need to do is understand the actual mechanism by which the reaction happens. Now, what you're seeing here is actually a proposed mechanism for a hypothetical reaction. So step one, A2 is reacting with D2 to make 2AD, and that happens to be fast, so that's got to be a fast reaction. Step 2 is AD reacting with BC to make AC and BD. That would also be fast. Step 3 is a slow reaction. And step 4 is another fast reaction. So what we have here is basically a proposed mechanism by which a series of individual collisions can lead to an overall reaction. If we add all these together and cancel, what we'd be left with is the overall reaction. Now, in a proposed mechanism, there's two terms that we're going to see from time to time that I want to make sure up front that you had an understanding of in a mechanism, and that's an intermediate. So what we have here are 4 elementary steps that have been proposed. Intermediates are substances that aren't in the overall reaction. You won't see them listed in the overall reaction, and that's because they only exist within the series of steps that occur. Now, an intermediate is a substance that's produced in one early elementary step and then consumed in a later step. So basically, it's a product first, and then later it becomes a reactant, so it disappears. That's why you never see it beginning and end, because it only exists in the middle of the reaction. Anything that behaves in that way would be an intermediate. Now, if you take a look at our top reaction, at the very first step, we create 2 ADs, and then both of those are consumed in subsequent reactions. AD reacts with BC, and AD also reacts with CD in a later step. So these would be examples of intermediates. They're not going to be in an overall reaction, but they are a part of the process in the middle of the reaction. So first appears as a product, later gets consumed as a reactant. Those would be intermediates. Now, BD follows the same exact thing. So BD first is produced in step 2 and then gets consumed in step 3. Now, when you take a look, do you see any other intermediates in this reaction? Look closely. I want you to take your time and find, is there any other intermediate existing? Sure enough, hopefully you found the fact that CD was produced in step 3 and then consumed in step 4. So this particular reaction actually has 3 different intermediates in our hypothetical equation. Now, the second thing that can happen that really occurs and is doing something in the middle of the reaction, but you don't really see it in the overall reaction, would be a catalyst. And catalyst is kind of different than intermediate. Intermediate wasn't there at the beginning and wasn't there at the end. A catalyst is there at the beginning and is there at the end, so it looks like it does nothing. But when you actually look at the proposed mechanism, it was actually something that was consumed in one step and then later produced, so it looked like it did nothing overall. So if it's used up in one step and then produced in a latter step, it does not show up in the final reaction. And remember, anything that appears first as a reactant and then later is consumed as a product would be a catalyst. Take a look at our reaction up here. And in the remaining substances, you should be able to find what our catalyst is. D2, a reactant in step 1, produced in step 2. So it disappears at the beginning and then reappears at the end. So in our overall reaction, it looks like it was there at the beginning and end. That's where catalysts appear in reaction mechanisms. Now, when we actually take a look at the individual elementary steps, one of the things that we're going to use to describe how those collisions are actually reacting is called molecularity. Molecularity is a process that tells how many molecules are involved in an elementary step. Now, termomolecular processes, term meaning basically three things colliding. So the simultaneous collisions of three molecules, think about it. If you're walking around in the hallway, what is the probability that at any one time three different people are going to collide in the exact same point? Highly likely that you bump into somebody from time to time, but it's much less likely that three things collide. And remember, collision theory, collisions don't occur without a collision. Termomolecular collisions are so unlikely, they really just aren't a valid part of any reaction mechanism because they're going to be too slow. They can happen, but they're going to be too slow to contribute overall to the reactions we're looking at. So the simplest type would be a unimolecular. Unimolecular is basically one thing decomposing into products. Bimolecular are very common. They're two things colliding. They can be the same thing colliding, A and A, or it could be A colliding with a B, and those would be bimolecular reactions. When you look at valid reaction mechanisms, you'll notice it's going to be a series of unimolecular and bimolecular things, because termomolecular and beyond, so unlikely it's just not going to be part of a valid mechanism. So then a reaction mechanism is really the sequence of events that describes the actual process by which reactants react with other things to become products. And when we put that together, what we're really doing is looking at what's called the reaction mechanism, the series of steps, the series of elementary steps that actually describes a reaction. A valid reaction mechanism really must agree with two things. So in an FRQ question or in a homework question, if you're asked, is this a valid mechanism, you need to think two things. First is, does it agree with the overall stoichiometry? And that basically is when you cancel all the intermediates and catalysts and add up and take a look at what's happening overall, does it equal the balanced molecular equation? If it does, then the stoichiometry is upheld. The second thing is it has to basically agree with experimentally determined rate law. So what you're proposing needs to agree with what we see in the real world. And that's something that we're going to look more closely at. So if we go back to our molecularity table, an elementary step, remember, is any reaction whose rate law can be written from its molecularity. So elementary steps are the actual collision process by which reaction occurs. And those simple steps, the stoichiometry of the actual substances involved in the reaction leads directly to order. So something that's an elementary step is not only a unimolecular or bimolecular way in which the reaction actually progresses, but the rate law can actually be written based upon the molecularity. And that's something we're going to exploit to take a look at how rate law is upheld in a certain reaction mechanism. So if you take a look at what's written up here, the rate expression of the elementary steps that we're looking at. Remember, we're basically only looking at these three situations up here because these are going to be our likely types of collisions and mechanisms, unimolecular and bimolecular. The rate expression, the rate law expression of an elementary step is given by the products of the rate constant and the concentrations of the reactants in the step. So it looks just like we did before, rate equals K times something. But what we're saying here is the coefficients in our elementary step of our reactants become the orders in our rate law. So in a case where you have a unimolecular situation, it's first order. When you have A reacting with A contributes to the rate, and so does the other A. That's an A squared situation. So a bimolecular between two A's would give us a second order relationship. Bimolecular with A and B, each A and B is first order. Overall, it's a second order. So bimoleculars are always second order overall. Unimolecular is always first order overall. So what we're really saying here is there's a connection between the rate law expression and the stoichiometry if something is an elementary step. Now, you need to understand what we're talking about here for elementary steps is not necessarily the case for the overall reaction. So this only is valid when we're looking at elementary steps. Because when we look at the overall reaction and the overall order of the reaction, it really makes a big difference. That whole fast and slow and where you're fast and slow, that has a huge impact on which concentrations actually appear as part of the rate law expression of the overall reaction. So be careful with that. Now, this is a movie about biomolecular reactions. It's going to be posted on the document manager part of my website. It's really short, but it does an excellent job of walking you through what's really happening on the particle level in collisions. So this really is a nice look at what's happening in a very simple reaction. So it's a very short, couple-minute movie, but it's well worth watching because it drives home the whole idea about what's happening in a biomolecular reaction. Now, first reaction mechanism problem that we're going to look at here. Nitrogen oxide is reduced by hydrogen to give water and nitrogen. So what we have here is a redox reaction between hydrogen and nitrogen monoxide to make nitrogen and water. Now, when you take a look at this reaction, the stoichiometry is 2 reacting with 2. Well, that would be implying 4 simultaneous collisions if that was an elementary step. The order of probability of that happening is so phenomenal, it's really unlikely that that would be a valid mechanism for how this reaction occurs. So what you're seeing is a proposed mechanism that would attempt to account for what we know about the reaction between hydrogen and nitrogen monoxide. So what we have is a proposed 3-step mechanism. Now, first thing I want you to do is look at the idea of molecularity that we talked about. If these are elementary steps, you should be able to figure out what type of molecularity they have. Now, in step 1, 2 NOs reacting to make N2O2. Well, this is a bimolecular situation because we have 2 things, 2 NOs reacting with themselves. It's a collision between these 2 things. It's not a straight decomposition of NO into something else. 2 NOs are actually combining. That's a bimolecular step. So that was the A plus A type situation. So be careful when it's written in this way. It kind of hides the fact that this was a bimolecular situation. Second and third steps are easy to see. We have 2 substances reacting. 2 things are colliding. They're both bimolecular. So A, what's the molecularity of each step? In this case, they all happen to be bimolecularity. That first one was a little bit tricky to see that, though. Now, the second thing we're going to look at is to show that the sum of these elementary steps actually equals the overall reaction. Remember I said that in order for a valid reaction mechanism to exist, it has to uphold stoichiometry and experimental rate law? Well, what we're really looking at here is, does it uphold stoichiometry? Now, if you take a look at this, what you're going to do is cancel out anything that is an intermediate or is a catalyst. So as you look through this reaction, NO is on the left here. Does that appear anywhere as a product? No, that's not going to cancel. But N2O2, my product of step 1, is actually a reactant in step 2. So N2O2 would be one example of an intermediate. So it's going to cancel out of our overall reaction. Now we've got H2. No, H2 isn't also on the product side, so that's fine. N2O, the next product. Yes, in the next step, N2O is consumed, so that's another intermediate. And then finally we have waters and N2. They don't appear on the other side. So I've canceled out all of my intermediates. I don't have any catalysts inside this reaction. So when I add things up, what I really get is I've got 2 hydrogens, I've got 2 NOs, and they're making an N2 and 2 waters. That's exactly what my top reaction was saying is actually occurring. So this proposed mechanism does uphold stoichiometry. So stoichiometry is proven in part B here. Now, part C, name the intermediates. Well, honestly, we just did that. Remember the substances we canceled a second ago? Those things would be our intermediates. So N2O2, dinitrogen dioxide, and N2O, dinitrogen monoxide, would be our intermediates in this reaction. And then D, what are the catalysts? Well, remember, we said we didn't have any catalysts because there was nothing that appeared first on the reactant side and later became a product. So there was none. Now, the next thing is reaction mechanism as it applies to rate law. So how do those 2 things come together? Because the second part of a valid reaction mechanism is that it upholds experimentally determined rate laws. So what's the relationship between those 2 things? Well, that's actually looking at that fast-slow idea. The slowest step in the mechanism is what's called the rate determining step. And the reason why it's called that is because it has the biggest impact in the overall rate. If you have a series of fast steps, something that happens in, a fraction of a second, and then your last step takes 30 seconds, yes, the individual steps contribute a little bit to your overall time, but what contributes most is that very slow 30-second step. So in every reaction mechanism, we're going to have a step that is significantly slower than the rest, and that would be our reaction mechanism, or our rate mechanism, or I should say our rate determining step of the reaction mechanism. The only way to find this is to really experimentally look at what's happening. You actually have to try and track what's happening in the individual steps. So you have to look at, in the last reaction when we had two NOs reacting, how fast or how rapidly was that individual step occurring. So the only way to find the rate determining step is really based upon experimentation. Now the rate of the overall reaction is limited by and is exactly equal to the combined rates of all elementary steps up to and including the rate determining step. So basically what you're going to be doing to use your reaction mechanism to look at the overall rate law is you're basically going to look at all your step speeds and find the slowest step and underline it. Everything before that line can be a part of your overall reaction mechanism. Everything after that line is going to be totally dropped. Now with this technique, what you're going to be doing is a real simplified version of this idea, but it works in the vast majority of cases you're going to run into in the AP test, and it's so much easier than the substitution method. So underline where the slow step is. And first thing you're going to do is cancel your intermediates, because the intermediates that appear in there aren't going to be a part of your overall mechanism. Now at that point, what you're going to do for each elementary step up to and including the rate determining step, you're going to write the individual rate law expression for each of those steps. So if the second step is your slow step, write the rate law expression for the first step and the second step. Now remember, if there's an intermediate that's been canceled out, that won't be included in that rate law expression for that step. And then once you've got that done, you're going to combine the rate laws to make an overall rate law. So if your first step is the slow step, the rate law expression of that first step is going to be the rate law expression of your overall reaction. Intermediates won't come into play because you're only looking at the reactants. So if it was a bimolecular slow step, then it's going to be an overall second order. If it was A colliding with A, it'd be an A squared. If it was substance A colliding with B, it would be the rate is going to equal K times the concentration of A to the first times the concentration of B to the first. So it'd be still overall second order. Now, if the second one is your slow step, remember, cancel your intermediates because something may be disappearing in that second step. And then do the same thing. You write the rate law based on the molecularity of the first step, write the rate law based on the molecularity of the second step, minus any intermediates, and then you combine the two. So if in the first step you had an A and a B, and the second step you had an A, and there used to be a C, but it was an intermediate, so it canceled out. What you'd end up with was an A and a B first order from the first step, and also an A in the second step. So when you combine the two, it's going to end up overall second order with respect to A, and first order with respect to B. So basically, you cancel your intermediates and you combine them together. So here's what it's going to look like. We're actually going to start with the one that we did before so we can skip through the beginning parts of this fairly quickly. So notice we've got the same proposed mechanism and we've got the same balanced equation up top. But there is something new mentioned, and that's because this has to be upheld by experimental evidence. The reaction between NO and H2 is believed to occur in the following three-step process. Same thing we said before, and then here's the new thing. Experimentally, the rate law is found to be the rate equals K times the concentration of NO squared times the concentration of H2. So it's second order with respect to NO and first order with respect to H2. In order for us to prove this is a valid mechanism and justify our answer, remember we have to meet two criteria. Does it match stoichiometry? And does it match our experimentally determined, that experimentally is a really important word here, rate law. So does it bear out to what we see by experimental evidence? Now, what we did before, I'm going to go through fairly quickly. The stoichiometry thing we've already proven. Remember, all you do is cancel intermediates and catalysts, add up to get the overall reaction. If it equals the overall mechanisms added equal the overall reaction, then we've proven the stoichiometry. So that's step one. Stoichiometry's been proven. Step two is a little bit more involved. And normally you'd have to do this by substitution. We're going to use a very simple method here. We look at what's left and we look at their individual rate laws and we stop when we get to the rate determining step. So this bottom one is immaterial because the overall length of the reaction has pretty much been determined before that thing actually starts. So you take a look at the first reaction. Remember, that was bimolecular, and that would equal rate equals K1 times NO squared. Remember, we had the two NOs hitting, so that would be an NO squared situation. Then we look at the second step. Now notice, this substance is gone. All we're left with on the reactant side is H2. So it's unimolecular with respect to H2. So that would rate equals K times H2 to the first, single order. So first order with respect to the H2 because there's only one. Now notice I put K1s and K2s. That's because the rate constants we're talking about for these individual steps is not the same as the K of the overall step. They're actually related to it, but that's something for a later chapter. We're not going to get into that here. So the next thing, combine the two. So when we combine, we would say the overall rate of the reaction is going to equal, those combination of little k's are going to equal our overall K. And then we have NO to the second, H2 to the first. Second order with respect to NO, first order with respect to H2. So using this technique, we have upheld the experimentally determined rate law. Remember, they said it should equal this. Well, we've shown that that is indeed what it equals. So if you're doing this on an FRQ question, or you're doing this on your homework, and you're justifying your answer, here's what you really need to say. So honestly, for the AP test, this is the key idea. Your answer must be written like this. Must, capitalized here. Because the question was, show that the proposed mechanism is valid. And what you really need to say is it's a valid mechanism. So we're saying it's valid since it agrees with both the stoichiometry and the experimentally determined rate law. Remember, the key is it has to meet both criteria, and you have to show it meets both criteria in your answer. So that's key, those words. Valid mechanism, stoichiometry is upheld, and the experimentally determined rate law is upheld. And you showed that in the previous slide that that was true. Next section, 14.7, gets into catalysts. Now, some of this you actually looked at in pre-AP, so some of this is going to be a little bit of review of old ideas. Now, catalysts, remember, increase the rate of reaction by decreasing the energy of activation. That's something we looked at in pre-AP last year. We also got into the fact that that fundamentally means then that you're creating a low energy pathway. So it used to take this much energy for the reaction to be effective. And when you look at the individual alternate pathway steps in the catalyzed situation, it's overall lower energy. So we have significantly lower kinetic energy giving us a valid reaction in this particular situation. So the catalyst changes the mechanism by which the process was occurring. It gives you an alternate pathway that the catalyst is involved with. Remember, it's there at the beginning, it's there at the end, but in the middle it's doing things. It's creating a low energy pathway that gives us successful collisions that wouldn't have been successful before. So because the catalyst is present at the beginning and the end of the reaction, you don't write it in the overall reaction. Remember, you always write it above the yield sign. But how does it participate in the reaction? Well, remember, it's consumed in one step and then later gets produced. So it looks like it's not participating, but when you look at the mechanism, you see that it does. So it's something that first appears as a reactant, gets consumed, and then later appears as a product again. So these elementary steps would not be present in the original reaction because there was no catalyst to react and cause those alternate mechanisms. So those new steps, which have lower overall energies of activation than the original large energy hill, makes the reaction happen faster, so it increases the rate of reaction. Now, intermediates are also not in the overall reaction, but that's because they're not present at the beginning and the end. So you tend to never see them unless you see the reaction mechanism. And that's because they're produced in one elementary step and then consumed in another. So you don't see them beginning and end. Now the next thing your books get into is that there's two fundamental types of catalysts. You should understand this vocab for my test as well as the AP test. Homogeneous catalysts are catalysts where the two things reacting, our catalyzing substance as well as the reactants, are in the same state. So if our catalyst is a gas and it's a gas reaction, it would be a homogeneous catalyst. Heterogeneous catalysts are like what you see in an automobile's catalytic converter. It's a term you've heard before. It gets its name because There's actually a catalyst inside there making the reaction happen. Heterogeneous catalysts, like inside the catalytic converter, have different phases. So inside the catalytic converter, you have a catalyst that's in the solid form, and the reaction itself are gases coming through. So they're in different states or different phases. So that's what a heterogeneous catalyst is when you have your catalyst in a different state or phase than your reacting substances. Now, one way in which a catalyst can speed up a reaction is really by holding the reactants together and helping the bonds break. So what it really does is it gives it a more effective orientation, so lower energy collisions still cause the reaction. An example of that would be in this particular case where you're seeing this solid substrate with gases that get attached to it. They're not being absorbed into the substrate. The gases are actually being stuck to the surface, and the surface allows the reaction to happen more easily. So that's one example of how a catalyst would work. Now, the video that was supposed to be there, that'll also be put on the site, that really takes you through an example of a heterogeneous catalyst type situation and shows you on a molecular level how that reaction I had on the previous slide actually occurs with animation. Next thing that your book talks about with respect to catalysts is enzymes. Enzymes are huge in body chemistry. They're one of the most important mechanisms chemically that happen inside your body because there's a lot of chemical reactions that would just happen to too slow to be effective. And either you're not going to lead to the breakdown of the nutrients your body is seeking in the time it goes through your digestive system, or maybe it's a reaction that needs to happen quickly to prevent a buildup of a certain chemical that become toxic in your body. Enzymes help in a lot of different biological situations inside your body. One of the most common ways to look at what enzymes do is what's known as the lock and key method of explanation or explaining enzymes and catalysts inside the body. And basically what you have is a large enzyme molecule. And that molecule, because of its geometry and attractive Coulombic attractions and so forth, and physical geometry, lends itself to grabbing and holding substrate molecules in very specific positions. And once it's held in that position, it gives it a better orientation so that it's more likely that reactions happen. So enzymes are an example of biological catalysts. And really what's happening here is the substrate fits into that active site of the enzyme, much like a key fits into a lock, and it helps orient that molecule to give it a better orientation for a more successful reaction to occur. An example of that would be lysosine, and the active site is this little cleft here in this area. And that little cleft can hold a substrate molecule like you see here, this yellow substrate molecule, in a very specific orientation that allows that substrate molecule to chemically react. So the substrate fits into that spot and forms the enzyme substrate complex, which is eventually going to become new chemicals in the chemical reaction. But the actual enzyme itself is still going to be there before and after. So through orientation of attractions and holding that molecule in a very specific orientation, it helps facilitate the reaction.